Hello, welcome to Applied Physics. My name is Sharma and I am your Applied Physics teacher. The course contents are prepared as per the first B.Tech Applied Physics syllabus of JNTUH, Hyderabad as per JNTUH R22 regulations. With this video, we'll start the first unit of Applied Physics, that is quantum physics and solids. In this video, we'll introduce the quantum physics. These are some of the great physicists who have made significant contribution in the development of quantum mechanics. They are Max Planck, Albert Einstein, Niels Bohr, de Broglie, Max Born, Paul Dirac, Heisenberg, Pauli, Schrödinger, Enrico Fermi, and Richard Feynman. In your previous classes, you might have studied about the celestial bodies such as Earth, Moon and Sun, etc. while discussing the Kepler's laws of planetary motion. You might have also studied the physics of rigid bodies under various aspects of physics. In all these cases, we have dealt with objects that are huge and massive. In the case of Kepler's laws of planetary motion, the celestial objects very massive and very huge. While in the case of mechanics, the rigid bodies are quite small when compared to the celestial bodies. The rigid bodies that we discussed in mechanics are several orders smaller than the celestial objects. Similarly, if you try to study the behavior of molecules, atoms, nuclei and other elementary particles, one will encounter new aspects of nature. And these new aspects of nature are commonly referred to as quantum phenomena, and the study of these quantum phenomena is known as quantum physics. So when you study the physics of molecules, atoms, nuclei and other elementary particles, we encounter new aspects of nature. These aspects of nature are referred to as new aspects because these aspects cannot be explained using the physics that you already learnt in your previous classes, or these aspects cannot be explained using the classical theories of physics. These aspects of nature are commonly referred to as quantum phenomena. A study of these quantum phenomena is known as quantum physics. And a mathematical theory of quantum physics is called quantum mechanics. So when you try to study the physics of molecules, atoms, nuclei and other elementary particles, one encounters new aspects of nature, and these new aspects of nature are referred to as quantum phenomena, and a study of these quantum phenomena is called as quantum physics, and the mathematical theory of quantum physics is known as quantum mechanics. While discussing the rigid body, we used to treat the rigid body as a single entity. Rigid bodies in mechanics are treated as single entities. But we know that each rigid body will have a very large number of molecules or atoms. So we do not treat the rigid body as a system of large number of molecules, atoms or other elementary particles. We only treat them as a single entity. Therefore, the laws of quantum physics that deals with the molecules, atoms, nuclei and other elementary particles, they will be the general laws of the nature. The laws of quantum physics are the general laws of nature. Reason being, we are dealing with the microscopic entities such as molecules, atoms and other elementary particles. Since we are dealing with the microscopic objects in the quantum mechanics, the laws of quantum mechanics are generally considered as the laws of nature. We shall now look at the limits of classical theories. Since we have said that the quantum phenomena start appearing in the case of microscopic objects, so there should be a limit beyond which we start observing the quantum phenomena and up to which we'll be happily using the classical theories. In order to understand the limits of classical theory, we shall recall the special theory of relativity. Please recall that while discussing the special theory of relativity, we used to have two different types of problems. A set of problems that are known as relativistic problems and another set is non-relativistic problems. We know the difference between these two. The difference is, in the case of relativistic problems, the material particle that moves with velocities that are comparable with c. So the velocity of the material particle will be comparable to c. And in the case of non-relativistic problems, the velocity of the material particle is very much less than c, where c is the speed of light. And we know that the speed of light c is the uppermost velocity with which a material particle can move. The value of c is 3 into 10 power 8 meters per second. And c is the upper limit of the velocity of any material particle and the upper limit of the velocity by which energy or information can be transmitted in physical space. So it is the upper limit for the velocity, energy and information transmission. So c is the uppermost velocity with which material particles can move, the energy can move and the information also can move. So if you have a physical system in which the material particles are moving with velocities that are comparable to c, that is the speed of light, then we call such problems as relativistic problems. Otherwise they are non-relativistic problems, which means c, that is the speed of light, is the deciding factor to designate a given problem as a relativistic problem or otherwise. So c plays the fundamental role in deciding whether a given physical system fits into the relativistic framework or otherwise. Now the question is there a natural constant just like c in special theory of relativity in quantum mechanics that can distinguish whether a given physical system fits into the quantum mechanical framework or otherwise? So we are looking at a natural constant like c in quantum mechanics. The answer is yes, we do have a natural constant. The natural constant is known as Planck's constant. It is denoted with a h whose value is 6.626 into 10 power minus 34 joule second. Please note that it is joule second but not joules per second. Now it is this value of Planck's constant that decides whether the given physical system fits into the quantum mechanical framework or otherwise. We shall look at the physical dimension of the Planck's constant. The physical dimension of Planck's constant are like this: time times energy, that is equal to length times momentum, which is equal to the angular momentum. The physical dimensions of Planck's constant are time times energy, length times momentum, which is moment of momentum. The moment of momentum is nothing but the angular momentum. Such a physical quantity is known as action in physics. Thereby, one can also say that the Planck's constant is the fundamental quantum of action. The Planck's constant is also known as fundamental quantum of action. Now we shall write a criteria to decide whether the given physical system fits into the quantum mechanical framework or otherwise. The criteria is: if for a physical system any natural dynamical variable, we shall discuss what natural dynamical variable is in a little while, which has the dimension of action and assumes a numerical value comparable to Planck's constant h, then the behavior of the system must be described within the framework of quantum mechanics. Here we have come across a new term called as dynamical variable. A dynamical variable is any variable which characterizes the state of the system. A dynamical variable is any variable which characterizes the state of the system. Here the state means a set of physical quantities such as a component of momentum, a component of angular momentum, a component of velocity, total energy, etc. A dynamical variable essentially is a variable which characterizes the state of the system. The examples are a component of momentum, a component of angular momentum, a component of velocity, total energy, a position coordinate of the system, etc. Now, the criteria is if for a physical system, any natural dynamical variable which has the dimension of action and assumes a numerical value comparable to Planck's constant h, then the behavior of the system must be described within the framework of quantum mechanics. In the early 20th century, three important problems in physics could not be explained successfully using the classical theories. They are blackbody radiation, photoelectric effect, stability and size of atoms, and many more other problems. With the help of quantum mechanics, these three problems and the other problems also could be explained successfully. Therefore, the quantum mechanics plays an important role in the modern physics. In this video, we have started our discussion by recalling the significant contributions made by great physicists, and we have said that when we try to study the physics of molecules, atoms, nuclei, and other elementary particles, new aspects of nature are encountered, and these new aspects of nature are generally known as quantum phenomena, and a study of these quantum phenomena is known as quantum physics. A mathematical theory of quantum physics is known as quantum mechanics. We have also stated that the laws of quantum physics are the general laws of nature. We have seen the limits of classical theory with the help of special theory of relativity. We have said that in the case of special theory of relativity, it is C that plays the fundamental role in deciding whether a given physical system fits into the relativistic framework or otherwise. In quantum mechanics also, such a natural constant exists. The natural constant is known as Planck's constant, which is denoted by h, whose value is 6.626 into 10 power minus 34 joule second. We have seen the dimensions of the Planck's constant. We have said that the Planck's constant is also known as the fundamental quantum of action. We have seen the criteria to identify a physical system to be called as quantum mechanical problem or otherwise. The criteria is if for a physical system any natural dynamical variable which has dimensions of action and assumes a numerical value comparable to Planck's constant, then the behavior of the system must be described within the framework of quantum mechanics. We have seen what dynamical variables are. We have seen the three important problems that could not be explained using the classical theories. They are blackbody radiation, photoelectric effect, stability and size of the atoms. We have said that these three problems and many other problems also could be successfully explained using the quantum mechanics. Therefore, quantum mechanics plays an important role in modern physics. Thank you.